Welcome to Honors Physics Podcast. This is the waves and pendulum problem set for periods 1 and 5 during AP testing week. We're looking at some multiple choice questions first. First, the total energy stored in simple harmonic motion is proportional to the what? Well, for a spring, our energy total expression is given by 1/2 Ka squared. Slightly different for a pendulum, but we can see right here what our answer should be, right? We have amplitude and squared, which gives us the square of the amplitude. Okay, it's pretty straightforward. Number 2, the simple harmonic motion is characterized by what? Constant acceleration. That can't be it, because if we remember our spring moving back and forth, right? Our spring moves this way, and then it moves this way, and as we move farther away from equilibrium, the acceleration increases, so that can't be it. Acceleration proportional constant to the acceleration of gravity, that can't be it either, because this is simple harmonic motion and there's nothing to do with gravity there. Proportional to displacement, okay. Proportional to velocity, no, that doesn't work, because that means that our velocity is the biggest here, but our force is the smallest there, or our acceleration is the smallest there, so that can't work. And also can't work here, so it must be that it's proportional to displacement, and we see then F equals negative kx, or ma equals negative kx, which gives us acceleration proportional to displacement. Okay, as we go through, doubling only the amplitude of a vibrating mass and spring system produces what effect on the mechanical energy of the system? Well, again, we remember that E total is 1/2 Ka squared, so if we double our A, we increase our energy by a factor of 4. Question 4, if you take a given pendulum to the moon where the acceleration of gravity is less than on Earth, the resonant frequency of the pendulum will do what? Well, we should remember that our frequency is given by the expression 1/2 pi times the square root of g over L. That comes from the fact that our period of this thing is 2 pi times the square root of L over g. And so now we see if we decrease g, we also decrease f. So it must be C decrease. Moving on to the back page, total constructive interference occurs when two waves with similar frequency and wavelength. Well, if we take a look, our frequency and wavelength being similar, so we wanted to have total constructive interference, which means we need our crests to line up with their crests and our troughs to line up with their troughs. So we'll look something like this, where this is wave A and this is wave B. If our crests line up with each other and the troughs line up with each other, that means that they are completely in phase with each other. For question 6, total destructive interference means that a crest lines up with a trough. So we end up seeing it goes like this, and then our opposite one goes like this. And since we are matching up a crest and a trough, this occurs completely out of phase with each other, so it must be completely out of phase. For question 7, with our mountain climber, their mass is 60 kilograms, they slip and fall a distance of 4 meters, at which time they reach the end of the safety rope then stretches, so we end up having a spring equation, or spring force. So if we looked at a free body diagram, when the person comes to a rest, we've got a mg down, we've got a kx up, so that means that kx is equal to mg, so our k is then equal to m times g over x, which is 60 times 9.8 divided by 2, which gives us, let's see, 294 newtons per meter. Question 8, a spring-driven dart gun propels a 10-gram dart. It's cocked by a force of 20 newtons over a distance of 5 centimeters. We're looking for the speed. Well, if we work backwards, we're looking for the speed, which means we would look for kinetic energy. The kinetic energy then comes from our potential spring energy, in which case we need the following. We need 1/2 K and x squared. We have our x, that's 0.05 meters. So all we need to do is find our k. But k can be found because we know F is equal to kx. So 20 newtons is equal to k times 0.05. So our k is then 400. So then our spring potential is 1/2 400 times 0.05 squared. That's going to equal our kinetic energy, which is 1/2 mv squared. Solving all of this, we get that v is equal to 10 meters per second. Question 9, our floating log is seen to bob up and down 15 times every minute. So that means that we have 15 waves in 60 seconds, which gives us 1 wave per 4 seconds, which is 0.25 hertz. And our frequency is equal to 1 over our period. So if we invert our frequency, we get our period, which means our period is equal to 4 seconds. And finally, a stretched spring is observed to have 3 equal segments in a standing wave driven at a frequency of 480 hertz. So what that means is that when we have this wave, we're given, this is what it looks like with 2 nodes at the very end because it's a standing wave in a string. So that means we have 1 1/2 full waves, which means our wavelength is equal to 2/3 of the total length of the string. If I called this my wavelength, or my length L, then this right here is my wavelength. In the next case, when we are looking for the 4, 1, 2, 3, and 4, this is the same length L. And here we have 2 wavelengths. So in this case, our wavelength is equal to 1/2 of our overall length. Since it's the same string, we know that our speed is equal to, our speed at 480 is going to be equal to our speed at the unknown, which means that lambda times our frequency at 180 or 480 is going to equal lambda times our frequency at our unknown. So when we keep going on with that, our lambda is 2/3 L for our 480 hertz, and it is 1/2 L for our unknown frequency. Our L's cancel out, which is good because we weren't given it, which gives us the following, that 4/3 times 480 is equal to our frequency. So the frequency that we have to oscillate this at is 640 hertz. And that is our in-class practice problem.